Hello everyone, welcome back to the channel. We are doing lead code 2410, maximum matching of players with trainers. So let's have a look at what the problem statement says. Now we are given two arrays. Number one is players and number two is trainers. Okay. Now players have certain ability which can be seen as part of the array, and then you have some amount of trainers and each trainer has a specific capacity. Now a player can be matched with a trainer when if its ability is less than or equal to the trainer's capacity. All right, so if the capacity of the trainer is, you can say, greater than or equal to the ability of the player, then that player and trainer can have a match. So for example, this one and this one can have a match, this two and this two can have a match. But then since this ability of the player is unmatchable, like no trainer has an ability which is equal to or greater than 3, there cannot be any matching, so this player remains unassigned. All right, at the end of the day this player remains unassigned. What we have to do is we have to return the maximum number of matching between the players and the trainers. So how can we do that? Now if we think about the simplest way of solving this problem, the brute force would be that, for example, I look at this 4 and I match it with the first trainer that I see is capable of coaching, of mentoring this player. So for example, I make this particular match, then I stumble upon 7, I see, okay, 2, 5, 8, all right. I make this particular match, and obviously 9 is not assignable, right? Because there is no trainer which has an ability which has a capacity which matches the ability of 9. Now, in the brute force approach, I would also have to take care of which trainer I'm assigning to which player, right? So, for example, I do not have a case wherein I have one trainer, but then I'm assigning that trainer to two different players, because that cannot be done. So there is one-to-one mapping on both the sides. Ith player can be matched with at most one trainer, and the jth trainer can be matched with at most one player. So I'll have to keep track of which trainer is being assigned to which player, and then I'll make sure that that trainer does not get assigned to any other player. Now, but then what's the you can say what's wrong with this particular approach? The wrong thing is, what I'm doing over here is I am traversing through the trainers array that takes O of n time, and I'm doing it, let's say players dot size is m, so the overall time complexity will be O of n into m. That's the first bottleneck that we are facing. But then even more importantly, the second thing is, let's say I'm traversing through the players array and also the trainers array. So for this particular 4, let's say what I do is I assign it to 9. All right, then I'm looking for a trainer for this 7. So as you can see, only 5 and 6 are left, so I cannot, obviously I cannot match any one of them with 7. But then when I stumble upon this 9, I cannot assign this 9 to any of these players as well. But then if I look for a different matching, if I, for example, match this 9 with this 9, and then this 4 with either one of these, either 5 or 6, so that way I'll be able to come up with an answer of 2, which is obviously greater than 1. So you see, that's actually where a brute force approach gets wrong. That is something where we can't just assign the first trainer that is legible for a certain player. So what I'm thinking is, why not always go for the, you can say, for the smallest possible candidate, for the smallest possible trainer, right? So what I will do is, rather than assigning 9 to 4, what I will do is I'll assign 5 to 4. So I'll keep traversing. I will keep traversing. Okay, this 9 is legible, well and good. Then this 5 is legible, well and good. So what I will do is, since I have found a shorter candidate as compared to 9, I will remove my marker from 9 and make 5 the new candidate for 4. And similarly, when I see 6, I think, okay, no, I have found a better candidate over here. So, why go for something bigger? Now, rather than traversing and finding the minimum, why don't we sort the trainers, right? This is something that obviously is going to come into your mind. So what I will do is I will sort these array. I will sort the trainers array and maybe also the players array in sorted order. So I will have 2 2 what was the initial array? I think it was um let me go and check it over here. It was 2588. All right. So 2, 5, 8 and 8. Now what I'll simply do is I will have two pointers, right? I will have a pointer over here, and I will have a pointer j over here. I will see, okay, if this trainer can coach this player, no, it cannot. So what I will do is I will increment my j pointer to here. Okay, can this trainer coach this player? Yes. So what I will do is I will match this particular trainer with this particular pair with this particular player and increment both I and j. All right, perfect. So this is how I'm going to go. And then the good thing about this is that we are always choosing the smallest possible trainer for any particular player. So for any particular player. So that's the benefit that that's going to give us is that, for example, this type of matching won't occur anytime, right? So then I have 7, I can assign it to this particular 8. So that's a match. I will increment my I and my j, and then this particular line cannot be assigned to anyone. So even if I increment my j, if I go and look for a trainer with a higher capability, I'll be out of bounds, right? And that is where my process is going to stop. So as simple as that, literally as simple as that, nothing too complicated, nothing fancy. And now let's see how we can implement this same strategy inside our coding environment. So let me put it over here like this so that we can uh, and let me also clear this up. Perfect. What I'm doing is, first of all, I'm sorting both the players array and the trainers array, right? So let me do that. Players dot begin, players dot end, right? I just copy and paste it below and sort the trainers array as well. Perfect. Then what I'm doing is I'm taking two pointers, one for the players, the other one for the trainers. That's good enough as well. And then basically I have a while loop. Now the condition obviously for that while loop is I don't want my I pointer to go out of bounds, right? I don't want this to go out of bounds and I don't want this to go out of bounds either. So if any one of them goes out of bounds, what's going to happen is I'm going to stop my process. So I'm going to say, and let's what we'll do is I'll say n is equals to players dot size, right? And m is equals to trainers dot size. Perfect. I'm going to say while I is less than n and j is less than m, we need to do something. We need to follow our two pointer strategy, right? And what that strategy was, it was something like this. So initially your ith pointer and your jth pointer, both of them are over here, right? Now you want to increment your jth pointer until and unless you find a trainer which is suitable for the ith player. Now this particular trainer is not suitable for the ith player, but then this particular trainer is. And you see, inside of this portion there could have been other twos and other threes as well. So you need to keep incrementing your jth pointer until and unless you found a suitable candidate, a suitable trainer. So what I will do is I will say, okay, while you can say while trainers of j, while trainers of j is less than players of I. Okay, what you need to do is just keep incrementing your j. And since you're incrementing your j, you need to check this fact that j should not go out of bounds. So j should remain inside bounds. And since right now trainers of j is, since it's less than players of I, just keep incrementing j. Now, you're going to increment, and ultimately you are going to stumble upon this particular 5, right? So you're going to say, okay, now I have found a particular matching. Then there can be a corner case. There can be a corner case, and we're going to look at it when the time comes. So now, since we have a matching, what I'm going to do is I'm going to increment my I, and I'm also going to increment my j. So what's going to happen is I'm going to keep my I over here and my j over here. Perfect. So since I is now at the second point, this tells me that, okay, one player has been already matched. So I don't have to, have a separate count variable, because this I itself is sort of, covering the fact that how many players are accounted for and how many of them are remaining at this point. All right, perfect. Now, again, I'm going to say trainers of J is less than players of I. That is not going to happen since players of I is already, less than trainers of J. So I plus plus and J plus plus, right? So I is going to come over here. The J is going to come at this point. And then what's going to happen is, since trainers of J is less than players of I, I'm going to increment my J. And at this point my J goes out of bounds. So at this point I do not need to increment my I because I'm out of bounds, right? So at this particular point, I need to take care of this condition that J should be less than M in order for both of these conditions to happen. All right, or in order for both of these conditions to happen. Perfect. And at the end of the while loop, when this whole process is done, I just need to return what my I is. So wherever I is, that basically tells me how many players have I covered. Like for example, in this particular scenario, my I is at the second index. That means that there are two players. Second index means there are two players, this 0 and 1, the 0th index and the 1 index, which have been covered, which have, you can say, which have found their perfect match, their trainer, right? So let's see if this strategy passes all the other test cases as well. It very clearly does. And if we think about the time and space complexity for this problem, then we can very clearly see that we are just iterating over the players and trainers simultaneously. So that is, you can say, O of n. In the worst case, I will have to go till the end of players and till the end of the trainers. So we can see that that's clearly O of n plus m. And if we think about the space complexity, then I'm not taking any extra space, but just these four extra variables. So the space complexity is going to be O of 1. So I hope you found the video helpful, and I will see you in the next one.